Bismillah, Alhamdulillah, wassalatu wassalamu ala Rasulillah. This is the last part of section 11.1 and it's about monotonic and bounded sequences. Uh, Sequences for which the term is always increase or always decrease play a special role in the study of sequences. So here a sequence an is called increasing if an is less than an plus 1 for all n greater than or equal to 1. So a1 is less than the term after it. So a1 is less than a2. The first term is less than the second term, and the second term is less than the third term, and so on. If this happens, then the sequence is increasing because when you go to the right, the numbers increases. So for example, the sequence n. This sequence, if n starts from 1, so it's 1, 2, 3, 4, 5, and so on. So the first term is less than the second term. The second term is less than the third term. In general, an, the nth term, is less than the nth plus 1 term. So the sequence would be increasing. It would be decreasing, the sequence would be decreasing if an is greater than, not less than. So the nth term is greater than the term after it, the nth plus 1 term, for all n greater than or equal to 1. So what would happen here? a1 is greater than a2, and a2 is greater than a3, and so on. So the highest or the greatest term here would be a1 because it's greater than all other terms. So for example, the sequence 1 over n. This sequence, if n is 1, starts by 1, the first term, and then half, then 1 over 3, then 1 over 4. So the first term is greater than the second is greater than the third, so this sequence is decreasing. If the sequence is increasing or decreasing, we call it monotonic. So what is a monotonic sequence? It's a sequence that's decreasing or increasing. Now, how to prove that a sequence is decreasing? So a sequence given like this and the question, prove that or show that or determine whether this sequence is increasing or decreasing. What to do? Well, you satisfy the definition. So the sequence would be decreasing if an is greater than an plus 1. So I need to show that an is greater than an plus 1. So I need to determine an first. What is an? Well, if this is the sequence, then an is the nth term, and it is 3 over n plus 5. Now, how to find an plus 1, the next term? Well, to find an plus 1, I replace n by n plus 1. So it would be 3 over n plus 1 plus 5. If I ask you to find a2, what would you do? You will say 3 over 2 plus 5. What did you do? You replaced n by 2. So similarly, if I ask you to find an plus 1, you replace n by n plus 1. So this would be 3 over n plus 1 plus 5, that's n plus 6. So now I want to prove that an, which is this one, is greater than this one. I always start from the denominators. Look to the denominators. I have n plus 5 and n plus 6. Which is larger? Of course, n plus 5 is less than n plus 6. Notice that n is a number starts from 1 always, because the first term is a1, the second term is a2. So in the sequence, n always starts from 1. If not, it will be stated. It could start from 0 or from 4 or from 5. Okay, but n always would be positive number. So n plus 5 is less than n plus 6. Now, if you find the reciprocal of n plus 5 is 1 over n plus 5. And the reciprocal of n plus 6 is 1 over n plus 6. Now, is the reciprocal less than? No, it would be greater than. Whenever you have, for example, 5 less than 6. Now, if you find the reciprocal, then 1 over 5 is not going to be less than 1 over 6. It is greater than. So 1 over n plus 5 is greater than 1 over n plus 6 because n plus 5 is positive, n plus 6 is positive. So 1 over n plus 5 would be greater than 1 over n plus 6. Now an is 3 over n plus 5. An plus 1 is 3 over n plus 6. So can I multiply this inequality by 3? Of course, 3 is a positive number. You can multiply by 3 without any problem. So what is 3 over n plus 5? It is an. 3 over n plus 6 is an plus 1. So starting from here, okay, this is the proof that an is greater than an plus 1. And this means that the sequence is decreasing. So I have proved here that the sequence is decreasing. Another question. Now, show that also the sequence is decreasing. So I need to show that an is greater than the next term, an plus 1. So when you go up, when you go to the right, okay, the 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 elements of the sequence becomes smaller. So this means that it is decreasing. Well, I need to find an. What is an? Well, an is given. If you try to find an plus 1, what is an plus 1? An plus 1, you replace n by n plus 1. Okay. And here you will have n plus 1 square plus 1. So you will have n plus 1 over n square plus 2n plus 1 plus 1 plus 2. So this is an plus 1. To prove that an is greater than an plus 1, I will start as usual from the denominators. Now what about n square plus 1 and n square plus 2n plus 2, which is larger? Notice that n is a positive integer. Of course, this is less than, because this is even n square plus 2, and this is positive. Okay. Now, if I find the reciprocal, then 1 over n square plus 1 is greater than 1 over n square plus 2n plus 2. Now, I need n here and n plus 1 here. So let me multiply by n. N is a positive integer, so nothing will happen. So n over n square plus 1 would be greater than n over n square plus 2n plus 2. Now this is an, but this is not yet an plus 1. So I cannot add 1 here without adding. So can I say can I say that this is greater than n plus 1 over n square plus 2n plus 2? Is this correct? If I add 1 to the numerator, is it is this making the fraction smaller or larger? When you add 1 to the numerator, you are increasing the fraction. So for example, 6 over 8 and 6 plus 1 over 8, which is larger. This is larger. So 6 over 8 is less than. So n over this is not greater than this. So using this method, I cannot conclude that an is greater than an plus 1. So I have problem trying to proving that this sequence is decreasing using this method, which is the method I used here in this exercise. So I advise you, whenever you have one n in the denominator like this, you use this method immediately. It would be easy like what we did here. But if you have n in the numerator and in the denominator, so it could be difficult, it could be not easy, it could be not possible to use this method to show that the sequence is decreasing. So what to do is, do you have another method? Yeah, of course. In calculus 1, we studied that if f prime is greater than 0, it should be written here somewhere. Okay. If it's not written, so I will write it. If f prime is greater than 0, if the derivative is positive, then the function is increasing. And if f prime is less than 0, then the function is decreasing. Let me write it. F is increasing, and here f is decreasing. This is what we studied in calculus 1. So to find out whether the function is decreasing or increasing, you find the derivative and you determine the signs of the derivative. And in the intervals in which the derivative is positive, f would be increasing, and when the derivative is negative, f would be decreasing. So I will consider here a function y equals, or f of x equals, x over x squared plus 1. And I will study the intervals of increase and decrease for this function. And to do that, I need to find y prime. And to find y prime, I need to use the quotient rule. And if you don't remember, the quotient rule says that to find the derivative of f over g, you write here g squared, and here you write f prime times g minus f times g prime. So let us apply this formula. So I have x squared plus 1 to the power 2. And the derivative of the numerator, which is 1, times the denominator, minus the derivative of the denominator, which is 2x, times the numerator. So I have 2x squared. So the numerator would be 1 minus x squared minus 2x squared is negative x squared. And here I will have x squared plus 1 to the power 2. Now I need to determine the signs of y prime, the derivative. Well, if you look to the denominator, it's always positive. X squared plus 1, always positive, to the power 2, always positive. And it has no real zero. No real zero. But the numerator is 1 minus x squared. And it has two zeros. If you put the numerator equal to 0, then x squared would be 1, and x is plus or minus 1. So I can determine the signs of y prime. The signs of y prime will depend on these numbers, -1 and 1. There will be three intervals from negative infinity to -1, from -1 to 1, from 1 to infinity. But notice that we need to find whether the sequence is decreasing and increasing. And notice that for sequences n start from 1. So really I need to know whether y prime is increasing or decreasing here in this interval from 1 to infinity. I'm not really interested in these two intervals. Anyway, you can find the signs of y prime and you can find out where y is increasing or decreasing everywhere. So you can just choose a number here greater than 1 in this interval, for example 2 or 3, and you replace it in y prime. If I choose 2, 1 minus 2 square, 1 minus 4 is negative, and this is always positive, so y prime here is negative. If you choose 0 in the middle, 1 minus 0 is 1, so you will find y prime here is positive, and if you choose -2, this would be 4, so y prime would be negative. So in fact, here y is decreasing, here y is increasing, and here y is decreasing. But I don't care about these two. I'm interested here. So y is increasing, not increasing, sorry, decreasing. Uh, I am interested in the last interval. Y is decreasing in the interval from 1 to infinity. So if y is decreasing, if the function is decreasing, then the sequence, this sequence, which is on the function, because f of n is equal to an, so an, the sequence, is decreasing on 1 to infinity on this interval, okay? Or for sequences, I don't say this, I say is decreasing for n greater than or equal to 1. So if you have n in the numerator and n in the denominator, and you want to show that the sequence is decreasing, find the function, write the function corresponds to the sequence, find y prime, and prove that y prime is negative in the interval 1 to infinity, then y would be decreasing, and then the sequence would be decreasing for n greater than or equal to 1. Now, definition of bounded above and bounded below sequences. A sequence is bounded above. It means that there is a number m above the sequence, greater than, m is greater than or equal to all the elements of the sequence. So for example, the sequence 1 over n, which is 1 half, 1 over 3, and so on. The sequence is bounded above by what? By 1, because 1 over n is less than or equal to 1. So capital M here is 1 for all n. For all n greater than or equal to 1, 1 over n, which is an, is less than or equal to 1. So this sequence is bounded above by 1. It would be the sequence bounded below if there is a number small m that's smaller than all the elements of the sequence. So for example, this sequence 1 over n, the limit of this sequence is what? When n goes to infinity is 0. So in fact 1 over n is greater than, it's not even equal. Of course you can write equal, it's no problem. But it's greater than 0 for all n greater than or equal to 1. Because all the numbers here would be positive, greater than 0. So this sequence, which is 1 over n, is bounded above by 1, and bounded below by 0. It's a bounded sequence. If the sequence is bounded above and below, we call it a bounded sequence. So 1 over n is a bounded sequence. Okay. Another example, the sequence n, 1, 2, 3, 4, 5. Well, it is bounded below by 1 because an or n here, an or n is greater than or equal to 1 for all n greater than or equal to 1. So an is n. Okay, what is n? Write the sequence. The first number is 1, 2, 3. For all the terms of the sequence are greater than or equal to 1. So it's bounded below by 1. But it's not bounded above because the term is continuous 4, 5 up to infinity. So this sequence is not bounded above. So it is not a bounded sequence. We do not call it a bounded sequence. While this sequence is bounded above and below. It is bounded above by 0 because the limit of n over n plus 1 is 1. The limit is 1. Okay. But it's clear what are the elements. Find the elements. The elements are if n is 1, 1 over 2. If n is 2, 2 over 3, and so on. So all the terms are greater than 0. So it's bounded below by 0. And the limit is 1. The limit of the sequence is 1. It approaches 1. But there is no 1. 1 is not one of the terms. And all of these numbers, 2 over 3, 3 over 4, and so on, are less than 1. So it's bounded above by 1 and bounded below by 0. It's a bounded sequence. Now, if the sequence is bounded and monotonic, it would be convergent. Okay, and that's a theorem. If it is bounded and monotonic, it would be convergent. So if it is increasing and bounded above, it is convergent, it converges. And if it is decreasing and bounded below, it's also convergent. Increasing and bounded above, so it's bounded above, so it will go to that number. And this sequence, which is n over n plus 1, is an example about sequence which is bounded above by 1 and it's increasing, by the way, because half, this is 0.5, this is 0.67, this is 0.75. So you can prove that it is increasing. You can prove that find the function because n up and n down, write the function f of x over x plus 1, and you will see that in the interval 1 to infinity, the derivative is positive. So it's increasing. And bounded above, so it will converge. Of course, it will converge to 1, the, 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 the bound of the sequence. And sequence that's decreasing and bounded below, okay, like 1 over n. This sequence is decreasing and bounded below because it's greater than 0. So it will be also convergent. Some questions. Determine whether the sequence is increasing, decreasing, or not monotonic. Is the sequence bounded? What do we know about cosine n? We know that cosine n is always a number between -1 and 1. Cosine and sine always between their graph y, the range is always between -1 and 1. So This sequence is bounded sequence. It is bounded above by 1 and bounded below by -1. But is it monotonic? Is it increasing or decreasing? No, it is not monotonic because you know cosine decreases, then increases, then decreases, then increases. Okay, it's not increasing or decreasing all the time. It goes up and down between -1 and 1. What about the sequence? Is it increasing or decreasing? Well, let us find an. This is an. Let us find an plus 1. We have n only in the denominator. So this would be 2 times n plus 1 plus 3. So it would be 1 over 2n plus 2 plus 3. That's 5. So let me compare an and an plus 1. Let me start by the denominators. What about 2n plus 3 and 2n plus 5? Well, this is less than this. So if I find the reciprocal, then 1 over 2n plus 3 would be greater than 1 over 2n plus 5. But 1 over 2n plus 3 is an, and 1 over 2n plus 5 is an plus 1. And if an is greater than the number after it, then the sequence is decreasing. And if it is decreasing, then it is monotonic. What about boundedness? Is this sequence bounded? Well, since it's decreasing, so what is the first term of the sequence? First term, if you replace n by 1, so it would be 1 over 5. The first term would be the largest term because it's decreasing. The next term, for example, would be when you replace n by 2. 2 times 2 plus 3, 7. So this sequence is bounded above by 1 over 5. Is it bounded below? Well, the limit of this sequence, 1 over infinity, is 0. So it's bounded below by 0. And 0 is not one of the terms. So this sequence is bounded and monotonic. So it is convergent. And of course, it converges to 0, okay, to the limit, because it has a limit and the limit is 0. Here I have n above and n below in the numerator and the denominator. So to show that it's increasing or decreasing, I need to work with functions. So f of x is 1 minus x over 2 plus x. And f prime would be quotient rule again. Derivative of 1 minus x is -1 times the denominator plus, sorry, minus, the formula is minus. The derivative of the denominator is 1 times the numerator, which is 1 minus x. So f prime of x is, I have -2 negative x and -1 plus x. X cancels with negative x, and I'll have -3 over x plus 2 or 2 plus x to the power 2. What do you see? I have square here, so the denominator is always positive, while the numerator is always negative. So this fraction is always negative. So f prime is always negative. This means that f is decreasing, always decreasing on its domain, the domain of f. And this means that the sequence an is decreasing for n greater than or equal to 1. Of course, the domain of f, all real numbers except -2. So from 1 to infinity, especially for x greater than 1, F is decreasing. So the sequence is also decreasing, so it is monotonic. Since it's decreasing, so it's bounded above by its first term. The first term is if you put in 0, it's half. Now the second term, if you put in 2, it would be negative. And all the terms after that would be negative. So it's bounded above by half. Now if I ask you to find the limit of 1 minus n over 2 plus n when n approaches infinity, we agreed to do what? To take the highest term with the highest power over term with the highest power. So the limit is negative 1. And this means that these numbers, when you list them, they approach negative 1, but negative 1 is not one of them. So all of them would be greater than negative 1. So negative 1 is a lower bound of this sequence. This sequence is bounded above and bounded below, so it's a bounded sequence. Okay, that's it. I hope you enjoyed sequences, the four parts of them.